Imagine you're taking a 50-step math exam. You start off strong. Step 1, step 2, everything is clear. But by the time you reach step 48, your brain feels overloaded. The sheer volume of numbers makes your working memory hit a wall. You're staring at the page, but the thread of the original problem has slipped away. It's a form of localized amnesia. Our working memory has strict physical limits. If we process too many details at once, our earlier thoughts get crowded out. It turns out that massive AI models, the ones behind tools like GPT or Gemini, run into this exact same problem. When an AI works through a long task, it generates new information at every step. As it thinks deeper, the noise of its current calculations drowns out the details it processed at the very beginning. This memory loss makes it difficult for the AI to handle complex, multi-step reasoning. To understand why, think of an AI as a detective solving a case across dozens of chronological steps. In the world of AI engineering, these steps are called layers. Under the old system, the detective has a terrible way of filing evidence. Instead of organizing the data, the AI shoves every new detail into one single manila folder. Layer after layer, that same folder is passed down the line, getting thicker and messier as it goes. Engineers call this signal dilution. By the final step, the folder is overflowing. If the AI needs to check a specific piece of evidence from the very first step, it can't. That original information is buried under a mountain of newer calculations. Because the folder is so stuffed, the final layers of the AI have to generate incredibly loud signals to be heard over the accumulated noise. If they don't scream, their newest insights get lost in the mess. This overstuffed folder creates a hard limit on intelligence. If you try to make an AI deeper by adding more layers, the noise eventually takes over, and the system's memory simply collapses. A research team at Kimi found a way to fix this by changing how the AI stores its information. They call it attention residuals. In our detective metaphor, the researchers take away the messy folder and replace it with a massive, highly organized corkboard. Every AI layer now pins its specific result to the board in a separate space. Upon reaching the end, the AI surveys the board for relevant layers, tying direct lines, like a red string, straight back to those early points, ignoring all the useless noise. By letting the AI pull specific details on demand, the system stays focused on the most important information. The amnesia is gone. But there's a catch. Scanning every single microthought would hit memory limits that could crash an entire data center. These models are often spread across different physical server racks connected by cables. If every layer is constantly sending individual data points back and forth across those cables, it creates a massive traffic jam that slows everything down. To make this practical, the team used a fix called block attention residuals. Instead of pinning every tiny detail, the AI groups layers into blocks, creating organized summaries for each. It still looks back, but now scans a few high-level summaries instead of billions of loose notes. The data traffic drops significantly. This tweak saves millions of dollars in computing costs. It makes it physically possible to train powerful models that can actually use this expanded memory. When the Kimi team tested this new design, the results were clear. These models outperformed traditional designs on difficult reasoning, math, and coding tests. We can see the difference when we look at how models perform as they get deeper. The blue line shows the old architecture, which hits a wall and collapses as more layers are added. But the red line, representing the new method, just keeps climbing. Because the AI can accurately retrieve its past thoughts, engineers can build much deeper models without the risk of the signal fading away. Depth is no longer a liability. It's an advantage that allows AI to follow long, complex chains of logic. The most fascinating discovery came when researchers mapped how the AI pulls this information. The resulting patterns look remarkably like a brain scan. For every single prompt, the system creates a unique pathway. The math automatically weights relevant past steps, while letting irrelevant ones fade away. This mirrors how our own brains work, constantly shifting focus and strengthening the connections that matter most in the moment. The AI isn't just following a static list, it's managing its own internal focus. These models now function as adaptive systems.
Every input triggers a new way to route information through the layers, letting the AI select the best internal path for the task at hand. And by fixing a simple filing system, researchers have moved artificial intelligence one step closer to the fluid way a real brain operates. To keep up with more jargon-free breakdowns of the latest tech, make sure to subscribe.